So, in the last class we were looking at resistance welding, right. So, we looked at all the variants of resistance welding. From resistance spot welding we move on to flash butt, resistance offset, okay, projection welding. Then we also saw the capacitor discharge welding, right. So, now we will move on to the next chapter. This chapter is on power beam processes. So, what do you mean by power beam? So, the beams which we actually use for a heat source, and they are made of optical rays, either laser or electron beam, and you can also consider plasma is also power beam. Okay, plasma is also neutral state, right. So, plasma beam welding is also a power beam welding process, where we can get a keyhole mode of welding carried out, because plasma itself it's a sort of a state of matter, right. So, we already looked at one of the power beam welding process, which is plasma welding, right. So, how we generate plasma, how we can get the keyhole welding by plasma. So, in this unit we are going to look at two optical heat sources. One is laser, the other one is electron beam, right. Okay, so, before going to that, again now we look at the introduction and the physics of this process. So, laser we use very commonly laser for welding, right. The first amplification is actually carried out on microwaves, and then it was actually transferred to more near infrared as well as the visible spectrum of optical rays. Because when laser was invented, so it was invented in huge labs, okay, labs in US, and people made fun of the scientists who invented, because what is the purpose of laser at that time? Okay, so everyone thought that, okay, so this guy is doing some fancy experiments and then showing that how light can be made into coherent, right. So, that is the property of laser, right, coherency. So, what is coherency? Same wavelength, okay. So, okay, that is monochromatic, isn't it? Okay, I mean when you say define coherency, how do you define? Parallel? Same? Yeah, same phase difference. Okay, so that is one point. So, what else should be the same? Phase difference would be the yeah, phase difference same means amplitude will be the same. Frequency, okay, vibration frequency should also be the same. Okay, and then these both the wavelength, wave path should also be the same. Okay, so then becomes coherent. Okay, so that makes one of the laser properties, okay, which is high power. Okay, because of there is no phase difference between the waves, and all carry same frequencies. Okay, the same wave pattern. That's why we call coherent. So, the moment you become, we make the beams highly coherent, okay, and then the light should also be not diverging, isn't it? Because if it diverges, then it loses its property. And it should also be collimated, isn't it? So, when you take a laser pointer and then point it onto a wall, the diameter remains the same, more or less, very small divergence in a conventional laser pointer, right. So, that means that they do not diverge, okay. So, it is collimated beam, and these properties make laser very attractive, but it was invented and no one thought, okay, laser can be used for something, but now we can't imagine life without lasers, right. So, like we use laser almost every day for some other purpose or some purpose, because we are looking at the display, so something is reading the hard drive, isn't it. So, laser is used to read the data. So, we use it for welding, but different power, okay. And for biological applications, the lasers are used for various, even Nobel laureates, this year Nobel laureates, they used lasers for various bio applications. They made suitable lasers for bio applications, that is why he got Nobel Prize, okay. So, without lasers we can't imagine the life, but it was invented and no one thought, okay, what is the use of laser, Okay, so see, one of the classical examples of academic research is we always say about the laser, because when scientists worked on to generate laser, I mean the research doesn't have immediate use, but 10 years by the time 1970 the laser started in commercial applications when the semiconductor industries started growing, right. Okay, good. So this is the history. So when the laser was invented in 1960, and then the welding, the use of lasers for welding already started in 1980s or so. Okay, so because the capacity of lasers is they grew by time. Okay, so because for welding applications we need to generate a large amount of power. Okay, for biological tissue applications, engineering, so you need few watts, whereas in welding we need a few hundred watts. Okay, so if you want to weld a 2 mm thick in a keyhole mode, you need at least 1 kilowatt, 1000 watts. Okay, so but we can generate lasers in various ways, right. So you must have studied in physics, right. So we will look at some of the introduction in this class, and then we will move on to the laser welding system, right. It's good. So what is so special about laser welding? So we use a very high intensity electromagnetic energy. Okay, that's why laser. So laser is very coherent, and you can manipulate the laser beam very easily. Okay, it is an optical ray. It can be transported from one place to other place using proper optic setups. Or nowadays we use fibers, so transport laser from one point to other point, and we can be manipulating the lasers very easily. Okay, so we can also access the laser in very sharp corners or in geometrically difficult positions, whereas in a conventional arc welding setup you need to have some geometrical limitation. Okay, whereas in a laser we can manipulate the beam very easily, right. And because of the highly collimated coherent beam, we can achieve extremely very high density, energy density, in a very narrow region, right. So if you have and I have worked on even 20 kilowatts laser, where the laser spot size less than a millimeter. That means that 20 kilowatts of power is focused on 800 microns beam. Okay, so such a high power can be concentrated onto a very tiny area. So the energy density can be very high. Okay, so for example, in using an fiber optics laser, the energy density can go as high as 10 power 10 to 10 power 13 watts per meter, square meter. Okay, 10 power 10 watts. So huge amount of energy can be focused on a very tiny area. Okay, whereas in arc welding case, in almost half of that. That's why the laser can be used. In fact, the electron beam also can be made into such a high energy density process, right. And how do we generate heat? Because these photons, the laser photons, they have a kinetic energy. Okay, when the kinetic energy, okay, is transferred to a workpiece, a metal, and the energy is converted into thermal energy. Because these laser photons, when it actually impinge on the sample, they get attenuated. Okay, so they get interacted with the base material, and during this process the kinetic energy of the photons are converted into thermal energy. Okay, we will see in subsequent classes the energy balance again in the physics. So that's the main heat source is laser photons, and the kinetic energy of these photons are converted into thermal energy, which is actually used to melt and then fuse the interfaces. Okay. In most of the cases, because of the very high energy density, the welding is carried out in keyhole mode. So you looked at already in plasma welding, right, keyhole. So through thickness hole we make the shape of keyhole, and because of that we can achieve very high penetration. Okay. And because the energy is concentrated very tiny area, so we can also achieve very narrow heat of exit zone. And because of the steep thermal gradient, the distortion can also be minimized significantly. Okay, these are some of the characteristic of these lasers, and most of the cases, because of very high density of laser beam, and we do not use an extra filler, okay, because we can melt enough to fuse the interface. So, most of the cases laser welding is done in autogenous mode. That means that we do not use any extra filler. Okay, so we can use laser as such. We can melt the entire interface, we can form keyhole, and then the interface can be welded. Yes, it is clear, right. So, this point is very attractive. So, this can be increased to several times higher nowadays, thanks to the invention of fiber lasers. Okay, because the limitation in the laser source is now reduced significantly, because we invented a new way of creating lasers using optical fibers. Okay, so, optical fibers can generate laser as high as I have seen in one of the labs in Japan. The laser power can go up to 100 kilowatts. Okay, so 100 kilowatts is a huge, humongous amount of power. So, whereas we had it in our lab, we are going to buy in IIT in our lab as well in end of this year, 4 kilowatt laser. Okay, so 4 kilowatt is good enough to have a full penetration of 8 mm thick steel. Okay, so 8 mm thick steel it can penetrate. Imagine if you have 100 kilowatts laser. Okay, so about half a meter you can melt easily. So, such high power lasers are used even for welding applications to weld some of the structures used for nuclear applications, because we may have to weld a large thickness, but it should not damage the workpiece severely, so that we minimize the stress development and distortion control. So, these kind of applications where we need a high energy density, the laser is very ideal, because it also gives us a very narrow weld zone and fusion zone. Sometimes this is not acceptable. So, when you have a very narrow weld zone, obviously you also have a very narrow stress concentration area, is not it. So, the cooling rates of this process is much higher laser welding. So, you may invariably end up getting a martensitic microstructure. So, if you have a very narrow weld zone, bulk structure, and that zone is actually the stress riser. Okay, so you end up partitioning stress very narrow region. So, in that case, sometimes it is not advisable to have a narrow weld regions when the structure is extremely loaded. Whereas, if you just want to need a joint, weld joint, the loading is not that severe, then the laser welding is very nicely used in those kind of applications. Okay, let us move on. So, what are the types of lasers we can have? So, in the welding generally is either carried out in a keyhole mode or conduction mode. So, what do you mean by the keyhole and conduction mode? I have already explained during plasma welding, right. So, keyhole mode is, so you will have suppose this is your say material. So, laser is actually impinge on the sample surface, that and then moment there is interaction happens, if a laser power is high enough, so you may end up penetrating something like this. Okay. So, the shape of the laser penetration is like a keyhole. Okay. So, if a power is high enough, so you will have a through thickness keyhole, and you will have metal vapor, which is actually causing the various force generation. So, we look at the force balance in the keyhole in later lectures, but now you can imagine that if the power is high enough, you can have a full penetration with the keyhole, or you can also reduce the power or defocus the laser in both ways, so that you do not melt the entire cross section, you will just melt at the surface. Okay. So, only this area is molten. So, this type of melting is known as doing welding in conduction mode, and this is done not to melt the entire cross sections for various reasons. For example, you just know you want to alloy or you want to change the surface condition. Okay, you want to deposit a powder onto a surface like in cladding. So, in that case you do not need to melt the entire cross section. So, you may use a very low power laser or defocused laser, and then you melt the powders and deposits on top surface. The laser can be used in conduction mode in that application. So that you do not melt the entire cross section, you will just melt only the top surface, right. And based on the laser source we can also classify the laser types, either the gas lasers, solid state lasers, diode lasers, or even fiber lasers. Okay. So this you must have studied already in our school days, right. So the most commonly used the gas lasers are helium neon and carbon dioxide lasers. And what do these gas do? So what is the purpose of having these classifying these gas, solid state, fiber, right? So what is
electrons go
so these are lasing mediums, okay. Okay, so the when you excite an atom, obviously the electrons in the ground state would be excited to an excited state, right. So when this excited state electron goes back to its ground state, the excited energy is released by emitting a photon, okay. And this bandwidth determines the wavelength of the photon, isn't it? So the bandwidth determines the wavelength of the photon. So this the lasing medium, the exciting medium, either can be gas or solid or even fiber. So if you use gas, so obviously the wavelength will be determined by the band gap, isn't it? The gap between the energy gap between the ground state and excited state. So that determines the wavelength. For example, helium neon and CO2 laser would generate a wavelength of 10 microns, the laser with 10 micron wavelength, okay. And you can also use solid state lasers. So most commonly used the laser source is Nd-YAG. So what is Nd-YAG? What is Nd stands for?
neodymium.
Yeah, so neodymium and YAG, yttrium, aluminum, gallium. What G stands for? So it's yttrium, aluminum, garnite. Okay, so yttrium, aluminum, garnite, and that can be used as a lasing medium, right. What is filling garnite? Right, and yttrium, aluminum, garnite's Nd-YAG is doped with neodymium. Okay, so that is a solid. YAG is generally doped with neodymium atoms. So then it becomes very stable laser medium. Otherwise, when you don't dope with neodymium, the stability of the laser source it goes down, because once it excites, it also loses its life. Okay, that's why we dope it with neodymium to increase the shelf life. Okay, so that we can the solid state laser source can serve for a long time. So when you use the Nd-YAG, the wavelength of the Nd-YAG, the laser is 1065 nanometer. And of course you can also use various diodes. So diodes can also generate lasers. So diode lasers, the wavelength can be varied from 800 to 980 nanometers. And nowadays we use optical fibers. Okay, so even the optical fibers in very latest development is we use graphene graphene mirrors in optical fibers to generate very high efficiency lasers with power going up to 100 kilowatts. Okay. And because the entire laser principle works based on the excitation of the electrons, the life of these laser sources is limited, except the fiber lasers, because fiber lasers they work in different principles than the gas or solid state lasers. So if you use a solid state Nd-YAG laser, say over the time you also lose the efficiency significantly, right, because the efficiency determined by the energy difference between the input to the output, right. So, over the time and the gas source as well as the solid state laser source, they lose this efficiency, because the moment you excite and then de-excite the electrons, and the material also degrades over time. Okay. So, the solid state laser, the laser rod, you will have to replace after 5 years or so. So, otherwise initially it may generate 4 kilowatts. After 5 years you would never reach 4 kilowatts because of the losing the erosion of the Nd-YAG crystals. Okay. So, we will end up losing the output power. So, after 5 years getting a 2 kilowatts in a 4 kilowatt system itself is very challenging. Same goes with diodes as well. Diodes also degrade over time in the excitation cycles. So, we will have to change the diodes. Okay. So, we will see one by one, and some of the basic principles. So, mainly fiber lasers we will concentrate, and because the gas solid state lasers, so they are actually going to go away in a few years time. So, we will all move on to the fiber lasers. Okay. So, the basic principle is the same for all. Okay. So, when the electrons orbit in its own orbital, and there will not be any release of photons. So, we send some energy to excite the electrons, and the moment the electrons are excited, so they are in high energy state, is not it? And then when you release the energy, the exciting energy, the electrons would come back to its ground state. And during this process, whatever energy is absorbed by this excited electron is released, and in various forms. One of the forms is a photon. You may also get X-rays, various things, but you may also get a photon released, and then these photons, when they release, can be made into highly coherent by using special arrangements. Okay. You need to have some reflective mirrors, and these mirrors can make these photons into high energy laser by increasing the frequency as well as by making them into a same path difference. Okay. And then becomes coherent, and once they become coherent and gain in power, and they can be released through a partially reflective mirror, and that is what you use it as a laser, is not it? So, the main purpose, the idea behind this process is to, so we give some energy which is known as pumping energy or pump photon. Okay. So, the pumping energy can be given by another laser itself. Okay. So, you may also use the laser itself, a small laser itself as a pumping laser to excite the electrons in the gas medium or solid state medium, and then the moment these are excited, and then you will have avalanche of excitations leading to a photon generation. So, these excitations, okay, can be brought into a ground state the moment you switch off the pump energy. Okay. So, very simple, right. So, this is the basic principle of the photon emission, and because we are stimulating this photon emission, okay, so that is why the laser comes from this. And then the stimulated photon emissions are amplified using a suitable mirror assembly, is not it? So, the simulated photons are amplified by having a medium in which these simulated photons are sent back and front, is not it? And during this process they get collimated, okay, they are made into coherent, and they are amplified into a very high power. And the moment you achieve a perfect collimation as well as coherency, and they can be made into go out using a partial mirror, and this mirror has a special reflective coatings and which can only send a coherent beam, right. So, that is how a laser medium work, right. And this laser medium can be gas, can be solid state, okay, can also be a diode, right. The principle is the same. Say for example, this is the gas source, say if you have CO2 or helium neon gas mixture, or you may also have Nd-YAG rods, okay, Nd-YAG rods containing partial and fully reflective mirrors, same principle. Okay. So, you will have a pump photon, pump energy or pump laser which would excite the Nd-YAG crystals, and during this process, so the de-excitation can lead to a generation of photons, and the moment photons are generated, okay, and they can be amplified using the mirrors and then collimated and increasing in power, and then using partially reflective mirror, these photons can be sent to a beam delivery, right. So, this is very simple mechanism of laser generation, right. Okay. So, in a fiber laser things are slightly different. So, in this case we do not use a medium. So, we use fiber optics, the fibers as a lasing medium. Okay. So, we sent a pump source to a clad optical fibers, and these pump sources are accelerated and then amplified and then coherent and then collimated using the reflective surfaces of these optical fibers, right. So, moment they are actually collimated and made into coherent, and they can be sent into another optical delivery system, and which can send the lasers to the workstations, right. So, most of the cases the pump source is using diode lasers, and these diode lasers sends the primary pumping laser source, and that source is sent into the optical fibers which has reflective surfaces, and so which are actually mostly doped with a highly refractive mirrors, mostly like gold surface. So, most of the cases the copper coated with gold. So, that is commonly used as a reflecting surface in doped fiber optical cables. So, and then the moment it becomes coherent and collimated can be sent into beam delivery system. The advantage of this the fiber optic system is the laser source is very flexible, is not it? It is a fiber. Okay. So, fiber is very expensive, by the way. So, 1 meter cost about 20 lakhs or so. Okay. So, it is very expensive. So, you get a fiber of 5 meters crore, right. So, you can, the longer the fiber more will be the beam coherency and then collimation and the high power obviously. So, if you want 4 kilowatts, you spend about 5 crore to get a fiber laser. So, you can get the fibers, and it is very flexible, right. So, you can also manipulate, and you can send keep the lasers somewhere else and then get it delivered. And for in an Nd-YAG system, so the Nd-YAG system itself is huge. Okay. So, if you look at the 4 kilowatt Nd-YAG, you need each Nd-YAG crystals can be made into 200 watts rods, and it also needs a pumping source. The pumping source can be laser or another lamp, diode laser can be. So, if you have a 4 kilowatt Nd-YAG system, so it will be off of this room size laser source, right, whereas in fiber can be in a small tabletop. Okay. So, it can be generating the same amount of power what you generate with such a huge system, and the efficiencies can be very high in optical fiber system, because in Nd-YAG system the pumping energy what you send, it is not all energy is converted into laser energy. So, efficiency is not even 5% laser efficiency. Okay. Any questions so far? So, how we produce lasers, right. So, it is very simple. Okay. So, it is not, there is no complex, and we do not spend much time in the laser production, because we assume that laser is produced and then we can use it for welding, right.